Hello everyone, my name is Wang Yizhou. I am a postgraduate from Nanjing Normal University. Today I am going to give a presentation on my paper. The title of the paper is A Parallel Sparse Approximate Inverse Preconditioning Algorithm based on MPI and CUDA. I would like to proceed with my presentation in the following four aspects. Introduction, SPI algorithm, optimizing SPI on GPUs with MPI, effectiveness analysis and performance comparison. In scientific research and engineering calculation, a core problem is how to solve large sparse linear equations quickly. Matrix A is an n-dimensional non-singular sparse matrix. For solving the linear system, we generally use iterative methods based on Kirchhoff subspaces, such as CG, GMUS, backstep. However, the convergence rate of these iterative methods often depends on the condition number of the matrix. The smaller the number of conditions is, the faster the convergence rate is. But in other cases, in order to speed up the convergence of iterative methods, it is often necessary to use preconditioning techniques. We multiply both sides of the equation by the matrix M, where matrix M is the approximate inverse of A. We define the matrix M as a preconditioner of the matrix A. There are many ways to construct the matrix M, such as ILU, FSAI, SPAI. Here we aim to optimize the SPI algorithm. The main contributions in this paper are summarized as follows. A general parallel framework based on MPI and CUDA is presented for optimizing the static SPI preconditioner, and is extended from one GPU to multiple GPUs. Only the CPU and GPU tasks are designated. Secondly, a strategy is presented to choose the optimal number of the threads for each column of the preconditioner. Thirdly, an optimization SPI preconditioning algorithm based on MPI and CUDA called hybrid SPI is presented. Before optimizing, I would like to give you an overview of the static SPI algorithm. As I said in the last section, we use a sparse matrix M, known as the preconditioner, to approximate the inverse of A, and M is computed by the following formula. Because matrix multiplication can be viewed as multiplying a matrix times a vector, the equation mentioned above can be separated into the following n independent least squares problems, where Mk represents a column of matrix M and Ek represents a column of the identity matrix. In order to have a clearer understanding of the process of SPI algorithm, which is also the calculation process on each GPU in the later optimization part, I will show you a simple example. Firstly, we are going to construct the array J and I, where J is the array of indices such that Mkj is not equal to 0, and I is a set of indices such that Aij is not equal to 0. For example, we construct J and I for the first column of the matrix A. Because we predict that the sparse mod of M is the same as that of A, we can know the position of the non-zeros in the vector M. Then, according to the above construction method, the specific contents of array J are as follows. So, when J is equal to 0, we can use this method to find a temporary array of I. In the same way, when J is equal to 3, we can find another temporary array of I. Then we may get the final array of I. After constructing J and I, we construct a submatrix slide A. Its dimension is equal to n1k times n2k, where n1 is the size of array I and n2 is the size of array J. Then the original problem can be reduced to the following formula. To solve this reduced formula, we decompose slide A into QR and get vector m by solving this equation, and then scatter to mk. At last, we may assemble the matrix M. Only after we understand the specific steps of the algorithm can we optimize it. The third part is the most important part of the paper. As mentioned earlier, one of the contributions of this paper is to present a general parallel framework for the optimization algorithm. As shown in the figure, the framework is divided into three parts, including pre-hybrid SP stage, compute hybrid SPI stage, and post-hybrid SPI stage. In the first part, we mainly propose a thread allocation strategy and determine the sparsity of matrix M. For any matrix, the number of threads Z for each column of the preconditioner is calculated by the following formulas. For example, if we get the contents of the array n2k, we can figure out what L is by saying that n2 max is greater than 32 and less than or equal to 64. Obviously, the lowercase l is equal to 6. Since nt is a fixed thread block of size 256, we can easily calculate the number of the threads Z for each column. In this case, Z is equal to 64. In addition, it is important to prescribe the sparsity of M. Mij is considered non-zero if the following formula is satisfied. And we can see from this example that the smaller the artificially defined parameter is, the more sparse M is. When the parameter is equal to 1, matrix M has the same sparsity as A. Before the second part, we need to know about MPI. It is a message-based interface used for data communication between processes. We then use MPI to call multiple GPUs in parallel to compute. Here is an example. Firstly, we assume that the matrix M and I have the same sparsity. Then, the structure of M is as follows. Then we are going to use 4 GPUs to compute, so we can divide the original matrix into 4 submatrices. Since each GPU has its own device number, and these device numbers can just match the thread number. So we can use MPI to have the process called the GPU for parallel calculation. That is the process of using multiple GPUs and MPI. It is worth mentioning that the calculation process of each GPU is unchanged, and because of the independence between the columns, each GPU only needs to know which column to start and which column to finish when calculating. The calculated vector M will be stored in a one-dimensional array on the respective GPU. Therefore, the post-hybrid SPI stage is to assemble M in the CSC storage format from multiple GPUs. Firstly, we transfer the vector M from GPU device memory back to the host memory. Secondly, we use the function MPI gatherv to integrate vector M into a one-dimensional array. The final result in array M is the non-zero elements of the matrix M, which is stored in CSV format. During the experiment, we tested 7 matrices. For each tested matrix, GPU P backsteps are called to solve the linear system on single GPU. The chart on the left is a comparison of execution time with the latest parallel SPI algorithm, and the chart on the right shows the proportion of hybrid SPI in the total computation time. Experimental results show that hybrid SPI is effective and has better performance than the other 3 algorithms used for comparison. For some matrices, the total time may not be significantly improved because of the small proportion of the preconditioning time in the whole calculation process. But for those matrices with slow preconditioning speed on a single GPU, the hybrid SPI will perform well. Thank you for your listening.